Welcome to the Explainer. So picture this. You're beaming high-speed internet from the middle of the woods using just a pizza-sized dish sitting on top of your house, straight up to a satellite orbiting out in space. When you really stop and think about it for a second, it's an absolutely mind-blowing technological premise.
But what makes it even crazier is the sheer scale and the speed of the whole operation. I mean, how exactly do you beam a reliable, high-speed connection from that little dish in the middle of nowhere to a target that's literally flying across the sky at 27,000 kilometers per hour? And maybe more importantly, how do you pull off this immense technological feat without relying on massive, traditional ground-based infrastructure?
Well, the secret lies in a sprawling network of thousands of satellites, orbiting just 550 kilometers away from the surface of the Earth.
Here's our roadmap for today. First, we'll look at the satellite internet revolution. Second, origins of the megaconstellation. Third, how Dishy reaches space. Fourth, the magic of beamforming. Fifth, global and orbital impact. And finally, we'll wrap up with the future of connectivity.
Section 2. Origins of the megaconstellation.
So the sheer difference in distance is really what makes all of this possible. Let's compare for a second. Traditional television satellites use a big parabolic reflector to catch broadcast signals from way out there, about 35,000 kilometers away. But there's a catch. They only receive signals. They can't send data back. Plus, at that massive distance, the latency, the time it takes for a signal to actually travel back and forth is just way too high for modern two-way internet. So SpaceX decided to place Starlink satellites in low Earth orbit, or LEO, at just 550 kilometers away. That closeness is a total game changer. It enables a 20 millisecond latency, which is exactly what you need for smoothly playing online games or just quickly surfing the web. However, because they are so much closer to Earth, their coverage area is way smaller, and that means you need thousands of them to cover the globe.
The rapid chronological development of this project is honestly staggering. In 2015, Elon Musk announced the Satellite Development Facility in Redmond, Washington. Then, by 2016, the company applied for FCC licensing, and SpaceX President Gwynne Shotwell laser-focused the team on a massive engineering hurdle, making those complex user terminals actually affordable for people. They launched their first 2 test satellites in 2018, followed by the very first 60 operational satellites in 2019. Astonishingly, by late 2020, they had already opened a public beta. It moved fast.
Section 3. How Dishy reaches space. Now, if we were to actually crack open one of these dishes, we wouldn't find a simple old-school radio antenna. Not at all. Behind that front panel is a massive printed circuit board. And arranged on this board, in this incredibly complex hexagonal honeycomb pattern, are 1,280 tiny individual antennas. Each little stack of copper circles acts as a single antenna, and the whole array is completely controlled by a network of microchips. Okay, so here's the crucial point. How does a flat dish track a satellite zooming overhead at 27,000 kilometers per hour? You're probably wondering, why not just use motors to spin the dish around? Well, while the dish does have motors on the back, they're really only used for the initial setup, just to get it pointed in the general direction of the sky. If the dish relied on physical moving parts to continuously track those incredibly fast satellites, the mechanical pieces would probably break within a month. And honestly, they simply aren't accurate enough to keep up.
Instead, the dish relies entirely on pure physics. Let's break down how just a single one of these 1,280 antennas actually works. A microchip sends a 12 gigahertz sinusoidal voltage, which is essentially a smoothly and rapidly waving electrical current, to a copper feed wire. This incredibly rapid oscillation pushes and pulls electrons in a copper patch above it, creating alternating positive and negative charges 12 billion times a second. As the current flows back and forth, it generates oscillating electric and magnetic fields. Because these fields push outward in sort of a balloon-like shape, an electromagnetic wave is born. But remember, a single antenna is tiny. Trying to use just one would be like turning on a single little light bulb in your yard and expecting someone on the International Space Station to see it.
Section 4. The magic of beamforming. Let's see how they solve that problem. The answer is beamforming, and it's exactly what it sounds like. When you have 2 antennas generating waves side by side, their waves naturally overlap. In some areas, the peaks of the waves point in the exact same direction and add together. This is called constructive interference. But in other areas, a peak meets a trough, and they effectively cancel each other out. That's destructive interference. By perfectly coordinating this across all 1,280 antennas on that circuit board, the dish creates a highly focused, laser-like beam. This constructive interference is so effective that it makes the main beam roughly 3,500 times stronger than what a single antenna could do alone.
But wait, we still need to steer that powerful beam without physically moving the dish, right? This is achieved through an absolutely crucial, software-driven technique called phase shifting. By slightly delaying the signal sent to specific antennas, shifting it anywhere between 0 and 359 degrees, the microchips change the exact timing of the peaks and troughs emitted from one antenna compared to its neighbor. This tiny shift instantly changes the angle of that constructive interference. By rapidly recalculating and applying these phase shifts every few microseconds, the dish can instantly and continuously steer its beam directly at a moving satellite without a single moving part. It's brilliant.
Section 5. Global and orbital impact.
This huge network has a really distinct dual nature out in the real world. On the commercial side, it has completely revolutionized connectivity for global shipping giants like Maersk and cruise lines like Carnival, keeping massive ships and airplanes connected basically anywhere on Earth. However, we're also observing some immense strategic implications. Starlink has played a vital communication role in modern conflicts such as the Russo-Ukrainian War and the 2026 Iran War. Because of this, SpaceX actually developed Starshield, which is a specific variation designed purely for government and military use. Now, this level of infrastructure naturally provokes a response. Researchers and military strategists in both China and Russia have actively published strategies focusing on countermeasures targeting the network. So it really highlights its status as a critical and sometimes highly contested geopolitical asset.
And the impact isn't just terrestrial. It's highly visible right up in the sky above us. You've probably seen photos or videos of the famous Starlink train streaking across the night sky, especially over Europe shortly after launch. With the network accounting for roughly 75% of all active maneuverable satellites in orbit, organizations like the International Astronomical Union have raised some highly valid concerns. These thousands of satellites create visible optical interference that leaves bright streaks across sensitive telescope images, and they can also cause radio interference. Both of these issues directly impact our ability to observe the deeper universe from the ground. So in response to these totally fair concerns, several objective engineering measures have been rolled out. To tackle the brightness issue, SpaceX has deployed solutions ranging from sun visors to special dielectric mirror films designed to darken the satellites. To handle the increasingly congested orbital environment, the satellites are equipped with Hall effect thrusters. These use tracking data to autonomously and smoothly avoid collisions, performing around 275 of these avoidance maneuvers every single day. Furthermore, to combat the very serious threat of space debris, 100% of the components on operational satellites are designed to completely demise, meaning they burn up entirely in Earth's atmosphere at the end of their life cycle.
Section 6. The future of connectivity.
Moving forward, the sheer scale of the hardware evolution currently underway is massive. The current generation of satellites, which are often called the V2 Mini, weigh up to 800 kilograms and are deployed using the Falcon 9 rocket. But the true next-generation Starlink V2 satellites? They are a completely different beast. We're talking about satellites that weigh 2,000 kilograms, are over 6 meters long, and feature incredibly massive solar and antenna arrays. In fact, they're so large that they require the immense payload capacity of the under-development Starship rocket just to get off the ground and into orbit.
So why build them so massive in the first place? Well, a major reason is the shift toward direct-to-cellular capabilities. By equipping these giant new satellites with massive, roughly 25 square meter antennas, the goal is to beam connectivity directly down to unmodified smartphones. Through partnerships with terrestrial cellular carriers, this effectively turns these massive satellites into roaming cell towers in space. The ultimate aim? To completely put an end to mobile dead zones across the entire globe.
We started all of this with a single pizza-sized dish just trying to find a signal in the woods. Now we are looking at a mega constellation that connects millions of homes, massive ships, and very soon, the standard smartphone sitting right in your pocket. It completely redefines our relationship with global connectivity. So I'll leave you with this final, provocative thought to chew on. As these networks continue to grow to tens of thousands of satellites, is there a limit to how much of our essential global infrastructure will eventually reside out there in low Earth orbit? Thank you for exploring this with me today. I hope you found this explainer as absolutely fascinating as I did.